To this class on marine hydrodynamics. In the last class, we have talked about some of the application of the Kelvins. Particularly, we have talked several application of the equation of motion, and today again we will continue the same. Now, before let me just point out few characteristics of the irrotational motion, and these are very essential, because one of the basic advantage advantage is that in case of irrotational motion, our flow is in the fluid region, the fluid satisfies the Laplace equation, where phi is Laplace equation, because the flow becomes potential type. Because the flow is a potential type, almost all characteristics of a potential function, velocity potential phi, will satisfy in the fluid region, and that is one of the advantage. And here I will just mention few of them in the context of the fluid flow problems. So, the first one in this series will be in irrotational motion, the velocity potential phi cannot be a maximum or a minimum. It cannot be a maximum or a minimum in the interior region The second one, when the motion is when flow is irrotational and all are in the context of a fluid flow problem, when flow is irrotational, the maximum value of speed, rather I will say, of speed, maximum value speed, it has to occur, will occur on the boundary. And the third one I will say, the pressure has its minimum value of course, this is if one is true, because we know that if we say the body forces are neglected, then P by rho plus Q square by 2 is equal to constant. The motion is irrotational and it is a steady motion. So, if we say that the speed is maximum, because P by rho plus Q square by 2 is constant, if speed is if in this case speed is maximum, automatically pressure has to be minimum. So, this is obvious from here, but I leave it to you to you can find this in most of the textbook on potential flow, or even if basic differential equation, partial differential equation books, where we talk about velocity potentials. These two results are very, and this is also a classical result in the theory of Laplace equation, that on the boundary the maximum or minimum value of a potential potential function will only occur on the boundary. It cannot have, and in fact the flow singularity, if anything is there, that will be only on the boundary also. It cannot be in the interior of this. This is a very, because one of the nice characteristics, nicety of the Laplace equation is that it is a function is a differentiable function and continuous function. So, inside the domain will not have any difficulty, because the flow is continuous, the velocity potential is continuously differentiable, On the other hand, the problem comes when it comes to the boundary, because if there is any singularity in the flow, that has to be always on the boundary. So, that is one of the, so always in many situations we always apply this when it comes to flow, particularly potential flow problems. Many times you apply a lot of many characteristics of this line integral, surface integral, volume integral, because the Green's theorem, which is the famous Green's theorem on converting line integral to surface integral, or surface integral line integral to surface, or surface integral to volume integrals, are based on the Green's theorem, and there the Laplace equation and the plays a very important role. It is the main thing is the Laplace equation in this case. So, for potential flow problems, whether it is a, today we are looking at marine hydrodynamics problem, any field where potential function velocity potential comes into picture, the Green's theorem plays a very major role. In fact, it was told that perhaps people working on physical scientists, particularly whether it is a electromagnetic waves or any continuum mechanics, one cannot ignore the name of Green's because of his theorem, and because every now and then one utilize the moment one look into a problem in potential flow or associated with Laplace equation, Green's theorem one has to apply. And in fact, in the marine hydrodynamics field, large class of problems where we assume the flow is potential, there Green's theorem we apply often to convert the from a complex domain, a 3-dimensional domain, to a 2-dimensional domain, and again from a 2-dimensional domain surface to a 1-dimensional line, and which makes our life easy, because computational we save a lot of computational time. And often this is the one of the main result, this Green's theorem, which use in various problems of fluid mechanics and mathematical physics. So, and I will point out here that often I use these symbols, these 3 symbols S and C. I always mean that when it is over a volume, even if I put a single integral, this is equivalent, actually it is the volume integral 3. On the other hand, when I look at a S, I always mean a surface integral, that means it is double integral. Whereas, in case of a line, either put as a line integral or call it along a C. So, this is a usual convention I am using in this lecture, which is often used in several books convention. This convention I will be using. I am using, and unless I specify, I will be using these 3 convention. Although I use a single integral, but I mean here a triple integral. Here, although I use a single integral, I mean it is a double integral, because it is a surface integral, and same thing happen in case of a line integral. So, with this understanding, now I will go back to the potential energy, particularly the kinetic energy. Just in the last class I was talking about the definition of kinetic energy, and in the definition I have already told you that the kinetic energy K associated with the potential flow is given by rho by 2 integral over S phi del phi by del n ds. This is the definition of kinetic energy. Now, with this I will go to Kelvin's, there is a result which is known as, some more results on this. Now, what will happen? This is my basic definition of kinetic energy. What will happen if in this, if this is also can be written as rho by 2, this is q square d tau. Now, if I say q is 0, if q is 0, that means my kinetic energy is 0. Further, which I will say, if phi is 0, then also kinetic energy is 0. and kinetic energy 0 means that means my q is also 0. So, there is no flow, and that too where phi is 0? Phi is 0 on the boundary. Similarly, if I say del phi by del n is 0, if I say on S, if del phi by del n is 0, then my kinetic energy is also 0, which implies my q is 0 also. That means there is no flow, which implies there is no flow. What we conclude? Irrotational motion conclusion. Irrotational motion is impossible in a closed simple connected region with fixed boundaries. The second conclusion I will say, this is one: if a closed vessel is brought to rest and of course, we assume the vessel is have fluid and fluid is rotational. Then also I will say the liquid, if a closed vessel of, rather I will say liquid, a closed vessel of liquid is brought to rest, assuming the fluid is rotational, then the liquid is also brought to rest. So, that means, if when I say this becomes on a fixed boundary, the boundary is not moving. When I say del phi by del n, the boundary is not moving, it is a fixed boundary. So, once the boundary is fixed, the velocity is fixed. That means, the fluid is brought to rest, and that is only possible only when the flow is rotational. So, these are two conclusions that is obvious from this definition of the kinetic energy for a rotational fluid flow. Now, I will go to Kelvin's minimum energy theorem. Let us start with the Kelvin's minimum energy theorem. It says that the irrotational motion of liquid, irrotational motion of a liquid occupying a simple connected region has less kinetic energy than any other motion consistent with the with same normal velocity on the boundary. So, this is let me say that suppose let T be the kinetic energy of the associated with the flow of an irrotational kinetic energy of the rotational motion of a fluid, and let phi be the corresponding velocity potential. And let T1 be the kinetic energy associated with any other motion. Then what will happen? My q bar will be the corresponding velocity q bar will be grad phi plus q naught, where del dot q naught is 0 because flow is incompressible, and n hat at q n because this is also 0 because it says that any other motion consistent with the same normal velocity on the boundary. So, q n, that is q 0, this is 0. Then what will happen to T1 kinetic energy associated with this, which will be half integral over tau rho into grad phi plus q naught square d tau. If I expand this, I can get this is gives me the kinetic energy associated with velocity potential phi, that is T, plus the velocity potential associated with it, the velocity T naught, that is T naught, plus what it will give me, plus I will have rho integral over tau grad phi dot q naught into q bar d tau. And just now I have used a result related to the velocity potential. I have used an identity. The identity says if I utilize this result, which I can always write related to q bar dot grad phi, where phi is the velocity potential, I can always write this is equal to T plus T naught plus integral over S rho times divergent of phi of q bar ds. Sorry, this is tau, so is d tau. And this one again, if I use it, I can always write a T plus T naught plus rho this one I can always use S into phi q 0 bar dot n hat ds. This is again, and this will give me, so this is my T1, that is the kinetic energy of any other motion. So, this is a quantity. If this is a surface, then q bar dot n hat is 0, this quantity will give me 0, and that will give me T plus T naught. So, which implies my T1 is because is greater than T, because for T naught is always greater than 0, because if there is a flow possible, kinetic energy has to be greater than 0. So, T1 is greater than T. This is what that means. If I have any other motion, the same region having same normal velocity on the boundary, then the T will have the less kinetic energy than the motion that is exist in the fluid. So, this is what I say, this is called Kelvin's minimum energy theorem. So, this is one of the very important characteristics of this kinetic energy. In fact, this definition of kinetic energy and these characteristics we use when it comes to water wave problem, particularly to always it comes to calculate the energy associated with the flow. When it comes to the energy, basically we have two energy, basically potential energy and kinetic energy. So, in that case we use this definition of, because in water waves most of the time we assume the flow is incompressibly rotational. So, use this definition of kinetic energy in terms of the velocity potential, and so it will come to this later in a big way when you come to water wave problems. Now, with this background, I will come to a very classical problem, and that is flow past a circular cylinder. And while from this flow past a circular cylinder, I will come to D'Alembert's paradox. That means, you have a fluid when the flow is incompressible and inviscid, then how you have the drag force acting on a body 0, and this remains as a paradox for a long time until the theory of viscous flow was well developed, and this remained as a paradox for a long time. That is known as D'Alembert's paradox, because it was the paradox says that in a uniform flow, if a cylinder flow past a cylinder, then the total drag force is 0, and this was a paradox for a long time. Let us come to see that how we will consider a uniform flow past a cylinder, and then we will derive that how the drag force will be 0. Now, let us come to that. Uniform flow past a circular cylinder. This is one of the very interesting problem of which is many times plays a very important role, and it is, suppose I consider the velocity potential phi is equal to u cos theta into r plus a square by r. Now, if I apply Contd, and suppose we have not given this phi, but what will happen to the flow here? If we have this is the phi, then we have to find what is the stream functions, and to find the stream function we have to go to the Contd equations, particularly in the cylindrical polar coordinate. In one of my past lectures, I have already told you what exactly the relations are. Del phi by del r is equal to del psi by del theta, and r del psi by del theta is equal to minus del phi by del theta. So, if we know phi, we can always get psi. So, by using these characteristics, we can always get this, we will get our psi as I am not going to the detail. This is u r 1 minus a square by r square sin theta. Given a phi this we can get. Now, what will happen? Where r is the, if I have a cylinder it is the radius of the circle, uniform cylinder which is along the z axis, whose axis is along the z axis. So, now if psi is this, what will happen? R is equal to a. If r is equal to a, psi is equal to 0, which is a constant. That means that means which means that is r is equal to a. If a is the radius of this circular cylinder, then at r is equal to a, this is 0, means this will, these are all, it can be, because psi is equal to constant and this, there is no flow across this. So, I can always consider there is a cylinder, the flow, there is a cylinder of radius r is equal to a. Now, what will happen when r tends to infinity? If r tends to infinity, then what will happen to my flow? What will happen to del psi by? Okay, I will come to this. Now, what will happen? Okay, before going to this, let us calculate what is q r, velocity in the radial direction. So, q r is a del phi by del r, and if I have del phi by del r, this is u cos theta 1 minus a square by r square, and what is q theta? The tangential velocity, that is 1 by r del phi by del theta, and that is again u sin theta 1 plus a square by r. So, this itself shows that when r tending to infinity, this part will be 0, this will be 0, and then you have q r is u cos theta, q theta is u sin theta when r is tending to infinity. So, now what will happen to q z again here, because I am considering a 2 dimensional flow. So, it will be del phi by del z, that is 0 here. So, as r tends to infinity, we have q r is u cos theta and q theta is u sin theta. Then what will happen to q r square plus q theta square root over, and that gives us u as r tends to infinity. Now, further I will just look at two things. What will happen at theta is equal to, and here all this I consider when you have a cylinder of radius a. Now, at theta is equal to 0, what happen? You have q r is equal to u and q theta is equal to 0. On the other hand, when theta is equal to pi by 2, implies q r is 0, q theta is pi by 2, so q r is 0, q theta is u. Now, what will happen to q square? Because I have been given the general definition of a q, that is u cos theta 1 minus a square by r square, that is your q r square, plus you have u square sin square theta 1 plus a square by r square. This is my q r, this is my q theta square, this is q r square, and that gives me, this will give me, if we expand it, this will give us u square 1 plus because sin square theta plus cos square theta, that will give you 1 plus a fourth by r fourth minus 2 a square by r square cos 2 theta. Because you will see that u square sin square theta plus cos square theta is 1, then you have, if you look at this term, a fourth by r fourth u square cos square theta, this is a fourth by u square sin square theta, so that will give you this one, and then here you get minus 2 u square a square 1 by r square, here it will give you cos square theta, here it will give sin square theta, so cos square theta sin square theta minus cos square theta, and that will give you minus cos 2 theta. So if this is the case, then we got q square is this, and which gives us q square is, what will happen when, this is the general expression for q theta, so it gives when theta is a, what will happen to cos theta is minus 1, if cos 2 theta is minus 1, which implies theta is equal to pi by 2, and q square will be, in that case, theta is pi by 2 and this 2 theta is minus 1. So in that case, this will be minus minus plus, so you have q is maximum. So here r is equal to a, maximum for r is equal to a. So what theta is equal to pi by 2, r is equal to a, the speed becomes maximum. So basically this flow will be looking like this. You have a flow, you have a circular cylinder, like this. This is cylinder of circle radius a. This is the origin. There is a fluid is flowing. This is a rigid cylinder is kept here. And in that case, what will happen? Now we have already seen that q square, we have seen that q square is 2 u square 2 u square, or rather I will say u square into 1 plus a fourth by r fourth minus 2 a square by r square cos theta. And what will happen when r is equal to a? If r is equal to a, that will mean my q square will be u square into 1 plus r is equal to a, means on the surface of the cylinder, this is 2, this is again 1 plus or minus, we have 2 cos theta, 2 cos 2 theta actually, cos 2 theta. So this is 2 u square 1 minus cos 2 theta, 2 u square to 2 sin square theta, which is same as 4 u square sin square theta, which implies my q will be 2 u sin theta. And if in the cylinder, if r is the radius of the cylinder and theta is this angle, so at any point on the cylinder, if p is any point on the cylinder and that is a theta, then my speed is given by this, the flow. Now, if I want to calculate the pressure, then I have to apply. So, this is the speed I got the flow characteristics. Now, if I want to calculate the pressure at any point, I need to apply, assuming body forces are neglected, we have from Bernoulli from equation of motion. We have p square by p pi rho plus q square by 2 is equal to constant. There is no body force. If body force is neglected, then this will be. Now, if I say that when the flow is, there is a uniform flow which is flowing to infinity, if I say pi be the pressure at infinity, pressure at large distance in the horizontal direction, at large distance, and let me say, because the flow is uniform, so let me say that, and already I know that u is the flow velocity. If u is the flow velocity, then I will have p by, at any point on the cylinder, you have p by rho. If I want to calculate the pressure, plus q square by 2 is equal to pi by rho, because I just equate the flow on the cylinder to any point u square by 2, and already I know on the cylinder. So, my p by rho, or rather p minus pi by rho is equal to u square by 2 minus q square by 2, and on the cylinder, on the circle, on the surface of the cylinder, my q is 2u sin theta. So, I have u square by 2 minus q square, that is 2u sin theta square by 2, and that will give me, so which give me see u square by 2 1 minus 4 sin square theta, that is my p minus pi by rho, which implies my p minus pi is rho u square by 2 into 1 minus 4 sin square theta. This is, so this p is the pressure at any point on the cylinder, pi is the pressure at infinity, fluid pressure, and this is u is the speed at infinity. So, which implies my p is pi plus rho u square by 2 into 1 minus 4 sin theta, sin square theta. Now, what will happen when theta is plus minus pi by 2? Theta is plus minus pi by 2. If theta is plus minus pi by 2, sin square theta will give me 1, which implies my p will be pi minus pi plus rho u square by 2 into minus, this is minus 3, which is pi minus 3 by 2 rho u square. So, what will happen? So, that means if the pressure has to be positive, the 0 pressure, when p is 0, p is 0 means pi equal to 3 rho u square by 2. If pi is less than, or so in general pi has to be greater than 3 rho u square by 2. If this is greater than this, if this holds, then only my p is greater than 0 on the surface of the cylinder. If on the other hand, if pi is less than 3 rho u square by 2, then p will be negative. So, that means under this condition p becomes negative, and in that situation cavity, because pressure becomes negative, and then what will happen? A vacuum will be generated, when pressure becomes negative, vacuum will be generated and there will not be any fluid there, and then once a vacuum is generated, that will form a cavity on the boundary of the surface. A cavity will be formed. This process often we call this as cavitation. When there is a negative pressure, cavity will be formed, and this process we call this as cavity. In fact, this problem occurs in the rapid moving tips. This cavitation, the formation of cavity is very common in case of rapid moving aircraft. Tips of a propeller blade. Formation of cavity often takes place in this situation. Now, with this understanding on cavity, now we know already the pressure. If we know the pressure, then what we can do, we can calculate always the force, because when I have derived this equation of motion, I have told that from pressure we can always calculate the force. Now, what will be the forces acting on this cylinder? That means we have two forces, one is the lift force and another is the drag force. And how to calculate the lift force? So, we will calculate the lift and drag force. We all know by now P minus pi is equal to rho u square by 2 1 minus 4 sin square theta, that is on the cylinder, the pressure on the cylinder, where u is the velocity at infinity and pi is the pressure at infinity. Now, what will L? L will happen minus 0 to 2 pi, because we are calculating on the circular boundary of the cylinder. So, this is start from theta can vary from 0 to 2 pi, and then it is P minus pi r sin theta d theta, and then that will give us, and negative sign we are taking because we are the lift is always in the, we are calculating the force on this direction, because always otherwise it is in the outward direction. So, that is why the negative sign comes. So, that will give us rho u square r by 2 into 0 to 2 pi 1 minus 4 sin square theta d theta, and in fact if you calculate this, you can find, oh, there is a r sin theta, sorry, sin theta d theta, 1 minus 4 sin square theta into r is gone sin theta d theta. Okay. So, this can be easily seen that 1 minus 4 sin square theta into sin theta d theta 0 to 2 pi, it can be easily seen that this is 0. So, the lift force is there. In a similar manner, this is the force that is in the vertical direction. In a similar, we will calculate the drag force, that is d, and it will be 0 to 2 pi P minus pi, that is r cos theta d theta. And that will again give us rho u square by 2 to r 0 to 2 pi 1 minus 4 sin square theta into cos theta d theta. And again it can be seen that this integral value is 0, which gives the total. So, when we have seen that both the the x component of the force per unit length is the x component of the force. Force per unit length, and this force is called the drag force, and this is the y component of the force. And this is called the lift force. This is the lift, this is the drag. In fact, we have found here both the lift and drag forces both are becoming 0, and once these are 0, that means there is the lift and the drag force both are 0, and which is quite contradictory, because it has been observed that the lift and drag force, the lift drag when there is a fluid is flowing and there is a cylinder, and then we are finding that the lift force is the drag force is 0, which is very contradictory, but contradictory in the sense that how can, because there is a force is acting on a body, and whereas the total force is becoming 0. So, this was initially predicted by D'Alembert. When we have a flow in a uniform stream, when a body is in a uniform stream, the total drag force, particularly when the body is submerged in the uniform stream, the total drag force is 0, and that prediction is a paradox, and that is known as D'Alembert's paradox. In fact, this remains because in the early days potential flow theory was well developed, and that time discuss major problems of application were based on the potential flow theory, assuming the flow is irrotational, and but this fallacy, because our prediction and but at the same time the experimental or model test results, they vary, that here that is showing, even if one can say from the one's own intuition also, that how can the force will be 0 when you have a fluid is acting on a body and you say the force is 0. So, that paradox remains until the theory of a viscous fluid was well developed, and after that it was proved that it was because the viscosity was neglected, and in this case viscous force was neglected, because of that it was showing the drag force was 0 and the lift force was 0. And on the other hand, if you include the, and that is one of the criteria I will say, that where the irrotational flow has failed here to predict the total force on a body. So, that is but this remains as a paradox, and this gives a good understanding about that irrotational flow is not, will not hold good for all kinds of problems. Of course, this irrotational flow, when the works for a large class of problem in fluid mechanics and other branches. In fact, when you will come to look at the motion of a ship in the water, or look at an aeroplane moving in the sky, in both the cases just surrounding the body, the forces are considered as viscous, and there we talk about the theory of boundary layer, but away from the body the forces are again considered potential type, because when the space is large, particularly the ocean away from the body, particularly the ship, the flow is taken as irrotational. Similarly, in case of aircraft, away from the aircraft the flow is considered as irrotational in nature. Particularly potential flow theory works very well, and similarly when you look at the force calculation on a pile type of structure in offshore engineering, a pile structure, here the drag force calculation and the lift force, we calculate the drag force and the lift force, where the viscosity plays a significant role. On the other hand, when you look at the calculation of forces on a large offshore structure, then the drag and lift force does not play much of a role. Sorry, the drag force, basically the viscosity is negligible, and in that case we always assume the flow is potential. So, we will come to that afterwards. So, today we have talked about some of the application of this equation of motion, and then we will in the next few classes we will spend several cases of the two dimensional flow under the assumptions that flow is irrotational in V-shade, and we will try to understand several flow characteristics. We describe several flows and understand their flow characteristics, and that will help, that will be helpful in understanding large class of flow under the assumption of the flow is irrotational and fluid is incompressible and invisible. So, today we will stop here and we will see in the next class. Thank you all.